Most people are familiar with the versatility of carbon. It is the backbone to life, figuratively and literally. Not only that, but carbon allotropes come in many shapes and sizes, as well as practical uses. For example, graphite is made of sheets of carbon bonded together in a flat layer, which are then weakly bonded vertically. When carbons are bonded together in a tetrahedral shape, it forms a giant molecular structure known as diamonds. And this is only two of many carbon allotropes, not to mention carbon's role in organic molecules. We can all agree that carbon is a vital and beautiful element, but today I would like to bring attention to an underappreciated molecule, the silica tetrahedra. This seemingly simple and random molecule is deceptively essential. Silicate minerals are the most abundant in the Earth's crust. That's right, this little molecule is everywhere beneath our feet. I'd like to take a couple moments to discuss and appreciate silicate minerals and their versatility. One structure in silicate minerals is the isolated tetrahedra. Each molecule is alone, then surrounded by other elements. One example is olivine, as seen here. The next is the single chain structure. The tetrahedra are bonded together in a line with one shared oxygen each, and elements fill in between the chains. One example is pyroxene. The single chain structure causes something interesting. The tetrahedra bonds to each other are strong, but their associations with the other elements around it are weak by comparison. This means when stress is applied to the structure, it will break in two directions at 90 degrees along those weaker associations. We can see this 90-degree pattern in the microscope perspective of a thin sliver of a single sheet structured mineral. This pattern of predictable breaking is referred to as cleavage. Next up is the double chain structure. This structure appears as two single chains bonded together at shared oxygens in the middle. Elements fill in between the double chain structures. An example of this is amphibole. The pattern of cleavage is similar to the single sheet, but because of the increased size of the silica tetrahedra structure, the two directions of cleavage meet at 120 and 60 degrees. The sheet structure is in some ways reminiscent of graphite, in that the tetrahedra bond together in a sheet with three shared oxygens between each, and then elements fill in between the sheets. An example of this is biotite or muscovite, both of which are classified as micas. Like graphite, the sheets tend to flake off together because they are stronger, causing the intra-phenomenon of thin sheets coming off from a larger structure, which is seen below. And finally, let's look at 3D frameworks. The tetrahedra are arranged in a 3D shape, reminiscent of diamonds. One example is quartz. Because the bonds are strong, it does not break in a predictable manner, resulting in uneven fracturing rather than cleavage. There is so much to discuss when it comes to silicate minerals, how structure impacts behavior, and the properties of the incredible variety of silicate minerals. Exploring more about these minerals is a valuable pathway because no matter our interest or passion, we all live on and thrive off of this earth.